I've got with me here today Ron Doetch. He is the founder of Solutions in the Land and chief agronomist of Feed Earth Now, the company responsible for the Terreplenish microbe. So I'll let Ron take it away.
Thank you, Charlie. Good morning. Today we're going to talk about Terreplenish, the mode of action, the background, and kind of how we got there, and really just some concepts about food and farming from that 30,000 foot level. So I talk about the future of food and farming because they are just one system. We don't have a food system and a farming system. We have a food and farming system, which means there's a lot of people that can vote on what that system consists of. Consumers have enormous power, and the choices that we make determine that food and farming system. So today I'm going to talk about leveraging natural services or ecological services or services from nature. So what I'm really talking about is the wind, the light, the water, or the weather. Weather is a natural service. We anticipate it, we forecasted it, but what we need to focus on is how do we leverage weather as an important part of our operation. Now, for those of you that are farming inside, you might create your own weather systems inside, but basically we're talking about outdoor farming, whether it's a patio tomato or whether it's a 10,000 acre field of corn. The size scale doesn't change some of the natural laws that we're going to talk about today. So I'm inviting you to look at your operation, whatever size it is or whatever type it is. Even if it's a window box and you're growing some geraniums, or a large industrial approach farming operation, you should look at your farm, your production area in 3 dimensions. We tend to look at only the flat surface of the soil, and soil is that thin layer dividing heaven and earth that provides all life. And if you say, well, what about the oceans? Yes, the soil that goes into the oceans perpetuates the life that's in our water. And included in all of that are living microbes. And today we're going to talk a lot about the microbes, kind of a microbiology 101 course. So when you look at your farm 3-dimensionally, we're going to be interested in what's going on in those different layers of the soil. But first, let's define what soil is. Soil is actually about 45% mineral, and hopefully it's 5% organic matter if the soil has been taken care of properly. And 5% organic matter is a good target. If you're 6 or 7%, that's great. It will increase the cation exchange capacity. But for all practical purposes, we're talking that soil is 45% minerals, 5% organic matter, 25% water, and 25% air. So when it rains, we get those weather events. The first thing that has to happen before water can grow into the ground is air has to leave the ground. The water is going to displace air, and if we don't have, if our soils are just compacted and hard and not have the tilth and the texture, water can't leave the soil. Air can't leave the soil, and water can't go in it. So if we look 3-dimensionally at our farm, our soil window box, we see that there are different layers. That first layer, the A horizon, is that which oxygen is readily mixing with. That dries out. It fluctuates on a daily basis. And then we go a little deeper into the B horizon. But what I want to talk about today is really our E horizon. And I'm missing a slide. The E horizon is what we call the leaching zone. It's where a lot of nutrients that we applied, a lot of sediment has silted out in our soil. And we're real interested in that area of alluviation or leaching zone. So if you want to think about that leaching zone, think about estuaries. An estuary is where salt water meets fresh water. And where the two come together and mix, that's where all shellfish life exists. It's lower in oxygen, it's a mixture of salt and fresh water. In the soil, we have that layer that is partially oxygenated, it's partly aerobic, partly anaerobic, and we are real interested in the microbes that live at that level. And one other comment I'll make about that level is as we farm, we change the depth of that layer. If we're in strict no-till, that E horizon could be as shallow as 2 or 3 inches. If we're deep plowing and using a ripper and other tillage tools, we may push the E horizon down 8 to 10 inches. But in that layer, we have a lot of microbial life that does a lot of things for us. And the bacteria that we're going to talk about today typically live in that area. So we hear a lot about mycorrhizae fungi. That term is being tossed around as some kind of a silver bullet, something you can buy and put in the soil, and all of a sudden you're going to have great big red lush tomatoes where you couldn't grow tomatoes before. So it's somewhat misleading. Our bacteria in Terreplenish are actually a mycorrhizae function, because the definition of mycorrhizae is a relationship between microbes and the roots. And we certainly have a relationship with the roots. When the plant emerges and begins to grow and shoots down secondary roots that want nutrition, all nutrition that's going to be absorbed into that plant is going to come from microbes. The microbes are going to metabolize that plant food and going to release it so where it's plant available. The tobacco plant is probably the most studied plant, and it's been found that the tobacco plant puts out 58 different sugars in chemical composition. It puts out specific sugars to attract specific microbes to bring them specific nutrients. So if your farm or your soil is low on boron, it will show up in a tissue test. And so when you go to correct that, the recommended rate is 100 pounds per acre. 1 acre of farmland, a foot deep, has 4 million pounds of soil. So we put 100 pounds of boron in 4 million pounds of soil, and the next time we tissue test, it says the plant has the right amount of boron. So how did that happen? How did that plant find 100 pounds of boron in 4 million pounds of soil? And the short answer to that is they didn't. It didn't happen. They exuded an exudate, is what we call them, as a little drop of sugar that's specifically designed to attract a specific microbe. And it is that microbe that brings the boron to the plant and exchanges that for sugar. And the microbes then want more sugar, and the plant will continue to exudate or make these little droplets of sugar to attract the specific microbes to get them what they need. So it's set of chickens, if you free range them, they will pretty much get everything they need. They will find all of those nutrients, and chickens have pretty complex needs for nutrients, and certainly our plants have complex needs for plant nutrients. So like a chicken, our plant doesn't have legs, it doesn't have wings, it can't go scavenger. So it employs those microbes to do that roaming work and foraging for the plant nutrients. So you can buy mycorrhizae fungi commercially available, but it's amazing to me that so many companies can sell something that's of a process. It's a relationship. So if you look at the ingredients on your bag of mycorrhizae, you'll find different things, because anybody can claim they can create a mycorrhizae function in the soil if they're doing something to improve soil health, if they're doing something to feed indigenous microbes. So the ingredients on this particular offering of mycorrhizae is biochar and a little bit of kelp, a little sea vegetable thrown in with the coal. And yes, biochar is just coal. If your soil needs coal, you could buy charcoal briquettes, grind them up and put them on the soil, and you could say that's mycorrhizae. It's a misnomer to think we're going to find a silver bullet in our microbes to counter the years and years of growing tomatoes or garlic in the same spot in the garden, and now we've crashed the soil. So we're going to go buy a silver bullet and correct all that. What we have to do is correct the soil. We have to correct the soil health, and we have to enlarge the microbial communities. So Terreplenish is a consortium of bacteria that we have settled on over time and selected to do very specific things. There's a million different microbes. There's a million different ways to put them together. There aren't a lot of secrets about what known microbes do in agriculture. We actually have a chart that lists hundreds and hundreds of microbes and their scientific names and what they do specifically when put in soil as an individual. But microbes don't live in individual communities. They live in a very lush, well-populated community of microbes. So a little bit of history on Terreplenish. We started field trials back in 2012. We were looking at the results of our selection of microbes. We did a lot of studies with greenhouse trials where we could do rapid increases in plants. We got over in Michigan with some blueberry growers. We started studying the reaction in compost. By 2015, we were looking at literally 100 different crops and how Terreplenish would react with those specific crops, including turf or lawn or golf courses. By 2016, we had included such things as alfalfa, apples, pears, etc. Plants behave differently to our microbe offering that we put in the soil. And our method of choice is to put microbes in the soil, because the brains of the plant have to be in the roots of the plant because they can't be anywhere else. And so the brain of the plant is going to develop this mycorrhizae relationship with these soldier microbes that's going to help them on with their life. And incidentally, microbes were here first. Microbes were here for millions of years before there was any other life on Earth. That was discovered in the 70s, not the 1670s or 1870s. It was Lynn Margulis in the 1970s that started to publish papers about this symbiosis or this relationship between plants and microbes. And we've now expanded that to include humans as the animal, because animals, plants, and microbes all evolve together. So we've been about 11 years now sorting out consciously some of these relationships. There are many offerings on the market today. We have a consortium that we've been comfortable with. We've tweaked it over the years. We've done and funded additional nitrogen studies, and we now feel confident that with the inclusion of microbes in our soils, we can generate about 40 to 60 pounds of plant available nitrogen in a growing season. And that applies to all plants that need and use nitrogen. We also use phosphorus solubilizing bacteria, which are known as PSBs in the industry. We have tremendous amounts of phosphorus in our soil. We just have a difficult time getting it into the plants because phosphorus likes to tie up with clay particles and is unavailable, although it shows quite high on soil test. We currently are doing some water infiltration studies to scientifically evaluate and measure how much more rainfall we can incorporate into the soil and the subsoil and ultimately into our aquifers from the high volumes of rainfall that we get every year here in the Midwest. So east of the 100th meridian, which goes through about the middle of North Dakota down through the middle of Kansas, everything east of that gets 30 to 40 to 50 to 60 inches of rainfall. Yes, Florida gets 65 inches of rainfall in a 6-month period. So east of the 100th meridian, or you can think of east of the Mississippi, although that's not correct, that would eliminate Iowa and Minnesota. But everything east of that, we have generally looked at how to get rid of water. Water is decidedly the scarcest element on the planet, and that's potable water, drinking water. We're going to see more and more emphasis put on how to harvest and store water, but obviously farmland is the natural place to both harvest and store water. We actually can store about 16,000 gallons of water per acre per 1% organic matter. And yes, by increasing the microbial communities in our soil, we will increase the water holding capacity by basically increasing organic matter over time. So if we had a 4% organic matter soil, we should hold about 64,000 gallons of water per acre. And that should carry most crops that we grow. We shouldn't be tiling fields, building channels to get rid of water because water is such a nuisance, and then turn around and have to irrigate through the growing season because we don't have enough water. So we have selected our microbes, as I mentioned, very specifically. The things that we're trying to accomplish with Terreplenish is to culture free living bacteria in the soil to provide at least half of the nitrogen needs of the plant. We've not been able to increase the amount of nitrogen we can make available yet, but it would be nice to be able to produce 100% of the plant's needs with free living microbes. I say free living because rhizobial bacteria that we've known about and worked with for a long time have to have, free living bacteria don't have to have a specific plant type growing like rhizobias. Rhizobias need the legumes, peas, beans, those type of crops to have a symbiosis with and live in the soil and convert atmospheric nitrogen to plant available nitrogen. Our atmosphere is 78% air. It's every 70, yeah, it's 100% air actually. Our atmosphere is actually 77% nitrogen, 21% oxygen, and everything else comprises that other 1%. So the other 9%, I'm sorry. So we try to replace the nitrogen in the soil and make nitrogen available. That happens to be a $16 billion industry in this country to make nitrogen available for plant production by using fossil fuels that obviously are non-renewable. So we can greatly lower our carbon footprint, but in terms of the financial health of a farm or plant production, the natural services that we can leverage will certainly lower our cost of production, which ultimately, to be sustainable, we not only have to take care of the plant and be accepted into the community, we also have to make money. So we choose the free living bacteria for nitrogen. We choose a bacteria for converting phosphorus. We use bacteria to break down cellulose and lignin. Cellulose and lignin are the most abundant element on Earth. And the reason for that is they're very complex sugars and they're difficult to break down. If you dig in almost any soil, you'll find plant residue that was a corn stalk or the outer sheath of a soybean plant or sunflower stalks. Sunflower stalks seem to be made out of plastic. They just don't want to go anywhere. So we have specific microbial bacteria to go in and break down that cellulose and lignin and make it available plant food for other microbes. Microbes, yes, need plant food besides the sugar the plant can give them. But we also have a large amount of sugar in the soil already tied up in cellulose and lignin. And as we've technologically changed our corn plant, we have a lot more corn residue in our farm fields than we used to have. And the industry has provided the solution for that is to buy Kevlar tires so that the corn stalks don't eat the tires off our vehicles. When in fact, we need to get the soil healthy to where it can break down the cellulose and lignin and make it available for other microbes to live on. In our consortium, by breaking down plant residue, we don't need to add additional microbial feed sources to our soils. It seems pretty natural that when growers decide to use microbial consortium in their farm, they want to feed them. They want to put down something to feed them. We're providing the food for our microbes by breaking down that cellulose and lignin. And that's true pretty much across the board. It's hard to find any good soil that doesn't have an abundance of cellulose and lignin just lying around. Our other large focus on our microbial selections is to fight plant pathogens. So we don't want to be using fungicides, insecticides. We can tank mix with herbicides, and that discussion's for another day. But we put in our microbial communities microbes that will specifically develop a branching mycelium to be present in a large part of the rhizosphere or that growing portion of our soils. And we suppress plant pathogens. So what I mean by that is on our chemistry that we commercially use as fungicides, we chemically try to kill microbes. The problem is we don't know which microbes to kill, but microbes that are beneficial microbes know which ones to suppress. They don't actually kill other microbes. They hold them in check. They compete for food sources. These pathogens are present, but they're not able to expand. I like to say that most plant diseases start in the soil. They start as a pathogen living in harmony with other microbes in the soil. And when favorable conditions get right, they put up a hypha, and through that hypha, they release spores. This sporulation then becomes an airborne pathogen that travels through your field and over to the neighbor's field, into the rain clouds, and come down someplace else. If you've ever grown oats, you can witness during the summer, a thunderstorm will come in, and the next couple of days, you'll have rust on your oat plants. Same's true of wheat. Where did that rust come from? it became an airborne pathogen. It came in with a thunderstorm, and we do use our product as foliar protection from airborne pathogens. But by far, our greatest success is to treat those pathogens when they're still in the soil. So this is one of our main workhorses. I say that, but all of our microbes are our main workhorses. This is from a microscope slide. We prepare our slides to see a very specific microbe. This slide was prepared to be able to see the azotobacters. And these aren't actually individual bacteria. These aren't rod-shaped bacteria. It's commonly held that rod-shaped bacteria in the microscope are pathogens. But in the case of azotobacters, when they see rough times ahead, they build what's called a cyst. And this cyst, which looks like a rod, is literally a cocoon harboring the vegetative spores of azotobacter. When conditions are right, these cysts will dissolve and release thousands and thousands and millions of vegetative spores that go to work. I like to explain that because people ask, what is the shelf life of Terreplenish? Our answer to that is 24 months. We actually have Terreplenish that we've held longer than 24 months, that's still viable and still test out as being a very high quality product. If you replace the cap and you don't mix water or oxygen with the Terreplenish that's left in the bottle, it literally will be good for 2 years. The reason that that's important is because when we treat crops, we don't always know what the plant is responding to. So if you put Terreplenish on your farm and there's an occurrence of a pathogen that's been released, it may appear that the application of Terreplenish has made your crop go backwards. And I bring that up because oftentimes people won't use the Terreplenish until they see powdery mildew on the leaves of their cucurbits or the vine crops. Vine crops, cucumbers, watermelons, squash, tend to get powdery mildew. When you see powdery mildew on the plant, the powdery mildew has already gone into the hyphae stage, released spores. The spores have colonized on the chlorophyll vegetation of the plant, and they're killing the plant. When you see them, you should have already treated them. So when we try to look at cause-effect relationships using microbial approaches, although highly effective, very cost efficient, it's different than what we've understood in the past about how things work. The chemical world has trained us to think about silver bullets, to think about one thing that did one thing, and yes, we can observe that that happened. We're working in systems. This is one of 13 microbes in our solution. They all have very specific roles in what they do, and they obey the first rule of consortia, and that is that one microbe cannot dominate the consortium, because then you would only have one microbe left. It would kill all the others. A lot of the intellectual properties around microbes is not the phenotypic identification of the microbe itself. It's which ones can be put together in what broth that they'll be ready to go to work when you open the jug, and they won't kill each other in the meantime. And it's a challenge. It's very difficult. And you'll see a lot of products on the market today that claim one thing. If you buy Serenade or Sonata, it is a single bacteria secondary metabolite. It will do one thing, and it will control some diseases. If you want nitrogen and phosphorus, you have to buy other products. So as we shift into microbial approaches for both crop production and crop protection, the industry is poised and ready to sell you 10 or 12 different products that do specifically different things. Although it's a challenge, what we have done is put them all together in the product that we call Terreplenish. So I briefly just want to mention water. I mentioned already that our microbes at Terreplenish will create higher water retention, higher water infiltration. As we convert atmospheric nitrogen to plant available nitrogen, we literally are taking atmospheric water out of the air with the nitrogen, and small amounts of that moisture are available to the plant on a daily basis. We're also traditionally thinking about, you know, the water hose or the big irrigation system where we go and flood the field with water. We don't need to mimic rainfall events with our irrigation. Plants take up water in minute amounts all the time. So when we put microbial consortium in the soil that converts atmospheric nitrogen and water, that water is made available to the plants on a daily basis in micro amounts, and it takes less water in doing so. So that's my message for today. As we use microbial approaches, we have to begin to think differently. With our big brains walking upright, we try to make it linear, but microbes aren't linear. They don't work in linear functions. They work in cycles. They work in systems. So I invite you to enter that world of microbiology and begin leveraging natural forces to make your crops more productive, more resilient, and lower your carbon footprint. Thank you. Questions?